Yeah.
Welcome, ladies and gentlemen,
Yeah.
to my presentation of our paper Preserving Consistency of Interrelated Models.
Yeah, because his voice is too low, we need to increase it. Yeah, it's
Oh,
maximum.
okay, maximum. Okay.
Let's try. How do I start?
Oh, start is
You should.
controlled by
Yeah,
mine.
please.
View-based evolution of variable systems. My name is Thomas Kuhn, and if you see this message, my live presentation has gone awry.
Okay, great.
When developing variable systems, we need to deal with variability in space, so by means of features that are usually mapped to artifacts that implement these features. When creating a product, these features are then selected and the corresponding artifacts are then built into the corresponding product. When a software product line is created, usually this software product line evolves over time. So the next generation of the car again reuses some of the artifacts and provides similar and additional features. And during the evolution, also these artifacts are reused and then refined. So we have two dimensions to deal with: variability in space and time. Now, the issue is usually variability in space is represented by mapping features to implementation artifacts, and variability in time is usually represented by changes or a version string by means of a version control system. However,
Hmm? Wrong.
variability in space and time is
It stops.
not managed in a
Okay.
uniform way using the same concept and same construct. So this makes life harder when tracing changes from a previous version of one artifact forward in time. So this feature and this artifact is reused throughout the different generations. Now fixing this is hardly doable without knowing where such a feature comes from, where the provenance is of the feature. Additionally, when thinking about more complex systems, so systems not just composed of source code, consider again a car. These systems are developed by using multiple different kinds of models. Again, not just source code, but also representations of the physical artifact, the physical product. Again, here is an example. Brake disc in a CAD model. And additionally, we also have models that combine the different information. So combine the information from the engine controller and the brake disc to, for instance, simulate the braking behavior. Now, obviously, there's shared information, so the engine controller's behavior should be reflected in the simulation model, and the brake disc size has an impact on the brake coefficient, also represented in this. Thus, meaning whenever of these models change, these changes must be reflected into the different models. Yeah, for instance, if a simulation model is adapted, the corresponding models must be kept consistent, or inconsistency must be highlighted. Additionally, when considering not just one product and the models used to develop this one product, but the huge variety of products in a product line, we also need to investigate which of these models are affected by this change. So how does this change propagate to the different variants and versions of the car? While the consistency between the different models can be managed, for instance, with the Vitruvius approach, where consistency is described by means of consistency preservation rules that whenever one model is changed, automatically adapt the corresponding other model. However, here again, the problem, current research approaches do not support the consistency preservation across the different models when variability is involved. So in order to overcome these issues, we propose a unified concept employing the unified conceptual model and the unified operations to deal with variability in space and time. Moreover, we augmented the proposed view-based operations with automated consistency preservation rules that can deal with interrelated models. So we investigated and provided means to propagate changes to the different variants, and we ensured that all the products stay consistent whenever a change is made to one of the variants. We implemented our approach prototypically using the Vitruvius framework, and for our evaluation of the functional suitability, we first employed the MobileMedia case study, and secondly, we extended the ArgoUML-SPL to represent both variability in space and time. In order to implement our approach, we refined the meta model and operations of the previous unified conceptual model and unified operations. We chose that our meta model reflects the expressiveness of feature models, so it could be easily translated to a feature model representation when investigating our variable system. So in our approach, constraints are either tree constraints or arbitrary cross-tree constraints. Additionally, we refined fragment to represent a delta module. Thus, our approach follows a delta-oriented approach to software product line engineering, meaning that any fragment represents a change to a base system, and such a delta can be an arbitrary addition, removal, or update of any of the model elements. Moreover, we realized the view-based unified operations externalize and internalize domain to get a view on the feature model of one system revision, and we use externalized product to get a view on one specific product given complete configuration. And when we change this view and make adaptations to this view, we use internalized changes similar to commit to push our changes back to the unified system. Here we need to provide a corresponding statement to which feature and feature revision this change is applicable to. Because this is a little bit difficult, let's look at a small example. Here we consider again an automotive system. In the first revision of the system, system revision 1, we have just the car feature. Now we use externalized domain to get an initially empty feature model, so only the root feature car is present. This feature model we can now adapt and extend to have an engine type with two options, either gasoline or electric, and an optional feature park assistant that can be used. We can internalize this domain. Upon internalization, a new system revision is created. All the new features are integrated into the automotive systems. Still, there are no implementation fragments there, so no deltas are present. In order to add deltas, we first need to externalize the product, now giving the corresponding features: car engine, engine type electric, not gasoline, and park assistant. Now our product view is initially empty, but we can create the corresponding artifacts. So here we, for instance, create a new engine controller with a base implementation, and the consistency preservation of Vitruve now permits to automatically generate the corresponding artifacts, for instance, in a SysML model, which we can then augment and extend. Once our product is in a consistent state, we can internalize these changes, again similar to commit. Here we provide the feature to which this change applies, so this update applies to. Here we state, so this belongs to the core feature, so this represents the base implementation of our car. And this change is now first creates a new system revision, a new feature revision for car, and the corresponding artifacts are represented as delta in our automotive systems and linked to this feature revision by means of a mapping. Later, we add new implementations in our product view. Here we add implementations specific to the electric engine. Again, the consistency preservation ensures that also the artifacts are present in the SysML model. Now we can again use internalized changes, but here we give the electric feature to announce that this addition corresponds to the feature of the electric engine. And last but not least, now we have a rather complete system, not fully implemented, but we can already externalize a new car with electric engine of version 1 and the original car 1 feature revision. In detail, how the system works is, again, consider we have one feature here, in this case ABS, and the corresponding fragments represented in blue as deltas. These represent changes. And if we spot an error in one of these features, we can use externalized product to get a feature representation. The feature selection now selects a set of deltas, delta modules, and using the Vitruvius approach, we perform all the consistency preservation rules and receive consequential changes. So all changes that need to be done to the corresponding opposite models. So if our changes affect only the Java model, then Vitruv computes all the additional changes that need to be done to the UML model in this example to keep both models consistent. Now on these models, developers can work by means of views, and we have first the source code view and the UML class diagram view. Now, if the developer chooses to change the implementation of the engine controller and fix the bug in the ABS, he can perform his changes. These changes trigger Vitruv, and again, original changes are translated to the consequential changes in the UML model. These are then performed, and the UML class diagram is kept consistent in the same way. Now, again, we can internalize these changes to create a new feature revision for the ABS feature. Now, as everything is back in the variable system, this feature and this feature revision with the update can now be used, not just by products with the electrical engine, but also products with the gasoline engine. For our evaluation, let's have a quick look. We investigated ArgoUML with 10 features and MobileMedia with 11 features, while MobileMedia already includes variability in space and time. We needed to extend the ArgoUML-SPL. To do this, we investigated the version history of the ArgoUML repository, identified 9 revisions, and in both cases we investigated and looked for feature interactions. We were interested in how many of the products will become inconsistent when such a change in the version occurs. First, obviously without consistency preservation, and second, when our consistency preservation approach is implemented and used. And we also want to investigate how much of the consistency preservations or how much of the repair operations can actually be done automatically. Our results surprisingly indicate that 26 of the 45 products of the ArgoUML-SPL became inconsistent when applying the different revisions. Similar for MobileMedia, 23 of the 27 products became inconsistent. However, in case of applying the consistency preservation rules, we could ensure that all revisions did not make any of the products inconsistent. Above that, we also found that none of these changes, none of these consistency preservation rules needed manual intervention. So all the repair operations be done fully automatically. After a quick look at the related work, I will not go into detail. We come to the conclusion, or we saw a unified approach for variability management in space and time that ensures the consistency not just between the different models, but also the different models used for the different variants and versions of the system. We provided a prototypical implementation integrated within the Vitruvius framework, and we evaluated the functional suitability. Thank you for listening to my talk.